We're going to go on and get started today. Today we are covering inverse matrices. Today we're covering inverse matrices. Now, one of the big reasons that we need inverses is because we cannot actually use division. Division is not possible with matrices. Office. Yep. We can't actually divide two matrices. It's just not possible. We cannot do that. But we can multiply by a matrix inverse. Will be the equivalent of actually dividing. Now, inverses also have other helpful uses with solving equations. Now, the first thing we need to talk about is the identity matrix. An identity matrix is a matrix with a diagonal of ones and everything else 0. So this right here is, by definition, the identity matrix for a 2 by 2. Now, for a 3 by 3, I'll scroll down here a little bit. It would look like this here, because we have a diagonal of ones and everything else is 0. Because it could even be for a 4 by 4. Because the big thing is the diagonal of 1 is going to make it the identity matrix. So no matter how big it is, as long as it is, identity matrix will always be square, and we have a diagonal of 1s, and everything else is 0, will be the identity matrix. The other thing that's interesting with the identity matrix is that whenever we multiply a matrix by it, here we're multiplying it by the right side on the right. It will be the same as if we multiplied it on the left. And it's just whatever the matrix is we multiplied by it. So essentially, multiplying by the identity matrix is the same as multiplying by 1. Now, the reason this is important is because whenever we look at two matrices, if we multiply them together and we get the identity matrix, it means that they are inverses of each other. Two matrices are inverses of each other if and only if their product is equal to the identity matrix, or here 1, 0, 0, 1. Is if we multiply them together and we get the identity matrix, they are. So if we want to find that out, if these are inverses, well, what we're going to do is multiply the two together and see if we get the identity. We're going to multiply the two together. And again, when we do multiplication, we're going over and down. So we're going to do negative 4 times 1/4 plus 2 times 1/2. Be the first one. Our next one is going to be over and down. So we'll have negative 4 times negative 1/2 plus 2 times negative 1. Our next one is going to be our over and down. So we could say negative 2 times 1/4 plus 1 times 1/2. And last but not least, we can go over and down, which would be negative 2 times negative 1/2 plus 1 times negative 1. So we're just doing the multiplication like we've done on previous. Yes, and the purple doesn't do well. It kind of just blocks the numbers out completely. Any questions on this so far? Well, now we can simplify this here and do negative 4 times 1/4, which is negative 1, plus 2 times 1/2 is 1. Here, negative 4 times negative 1/2 would be positive 2. Let's focus up here, Caleb. Our next one is going to be 2 times 1/4, which will be negative 1/2, plus, well, 1/2, because 1 times 1/2 will be 1/2. And the last one, negative 2 times negative 1/2 will be 1. And 1 times negative 1 would be negative 1. What do we get for each number? Then it works out they actually all became 0. So are these two matrices inverses of each other? No, because we did not get the identity matrix. Because if this was to work, we needed yellow. These two zeros here to be 1. Because if both of those were 1, we had a diagonal of 1. We would have the identity matrix, and they would be inverses. Any other questions on this here? Could we have done this in the calculator? Well, yeah, the calculator will do multiplication, yes? So let's do it in the calculator for this one here. Oh, note sheet. Clear. I'll clear out the key history. So, if we want to type this into the calculator, we need to see, is their product the identity matrix? So for starters, we can go second matrix, edit, and input F for A. So that would be a 2 by 2, and we would have 3, negative 5, negative 2, and 6. And that would be the first mix. Now at this point, we can go second matrix, over to edit, and down to matrix B, which is a 2 by 2. Now we can type the numbers in. And I already have them typed in apparently. Here as our fractions. Now to get the fraction, we can go alpha y equals, enter, and say 3 over 4. Enter, and type each one in using that. Alpha y equals enter. We could also, instead of doing that, we could say 5 divided by 8 and write it as a fraction, or just do the division itself. Either way works just fine. 1/4 and 3/8. Is there any question typing these in? So we need them multiplied together. So I can go second matrix A, and then second matrix B, because when we put them next to each other, it understands that we are talking about multiplication, and we can hit enter.
Oh, that looks like it says Caleb.
And we get the I do, yes. So are these two inverses? Well, yeah, because if we get the identity matrix when we multiply them together, we will get the identity, because they are inverses. So if two matrices multiply together, when multiplied, we get the identity matrix, then they are inverses of each other. Let's try it the other way, because when we did multiplication, well, when we multiplied 2 one direction, and we flipped it, it gave us a totally different answer, yes? So let's see what happens if I do matrix B times matrix A. I flip it. I get what? Same thing. Because if two matrices are inverses of each other, the order in which we multiply them doesn't matter. They're still going to be inverses of each other. It works either way. Questions on this here? So this would be yes. thank you. Any other questions on determining whether two matrices are inverses of each other? Mm-hmm. Be ready for the next piece. Finding the inverse. Finding the inverse. The inverse of matrix A, which is defined here as A, B, C, D, is A inverse. A to the negative 1, we pronounce that as A inverse. Now, for A inverse, we are given this equation here is equal to 1 over AD minus BC times D negative B negative C A. And this is the inverse of A, which is the matrix A, B, C, D. Does the denominator of this fraction, AB minus BC, does that kind of look familiar? Because it should. Well, it does. Well, the other direction, yes? Because we did that a few days ago, because it was our 2 by 2 determinants. So really, this here is saying that's just 1 over the determinant of matrix A. So we're taking 1 over the determinant, or we can just say AD minus BC this matrix. Well, what happened to A and D? They switched, and B and C became negative. So we were going to switch A and D and make B and C negative, or we're going to change the sign. And that's it. So also, the determinant cannot be 0. If the determinant of a matrix is 0, it's not invertible. It does not have an inverse. If a matrix determinant is 0, we cannot have an inverse of it. It does not have an inverse. This looks complicated? A little bit? It's not as complicated as you might think. Let's say the inverse is equal to 1 over. What numbers are in A and D's places? 7 and negative 1. So we're going to have 7 times negative 1 minus, well, B and C are negative 5 and 2. Okay. That's the first part. Now, inside the matrix, we said that A and D switch places, yes? So A is 7 and D is negative 1. Switch them, though our first number is negative 1 and the bottom corner is 7. They flip. And we said that B and C became negative. We switched the signs. So in B's spot is negative 5. Our new one is positive 5. In the other space, we have positive 2. And over here, we're going to have negative 2. Any questions on this here? Okay. Well, the next thing we need to do is to simplify the denominator, the bottom of this fraction. We could type this onto a calculator and it would give us the answer. Or we can do it by hand. 7 times negative 1 is negative 7 minus negative 5 times 2 is negative 10. But negative and negative would make a positive. So we have negative 1, 5, negative 7. Well, what is negative 7 plus 10? 3. Now we just need to multiply each term in the matrix by 1/3 and we're done. So negative 1 times 1/3 is negative 1/3. 5/3. Negative 2 times 1/3 is negative 2/3, and 7 times 1/3 is 7/3. And that's it. That's all we have to do for this here. A little bit easier than you thought this was going to be. So really for these inverses, we just plug in A, B, and C's values, simplify, and we're done. And that's the inverse. Huh? Any questions on this here? We're ready for the next one. Okay. Well, let's just go on and plug this in for Q inverse. Good. We can. Let's do this one by hand with the next one in the calculator. Is there something I want to show with this one? So our first numbers would be -8 times 9. And then we'd have -6 times 12. Because our determinant would be -8 times 9 minus -6 times 12. Heads up, boys. Thank you. Now, at this point, we're going to switch A and B, so that would be our -8 and 9. Would switch places. Now, the -6 is going to become +6, and the 12 is going to become -12. A and B flip. B and C become negative, or they switch signs. Okay. Now let's simplify the bottom of that fraction. -8 times 9 is -72. -6 times 12 is -72. 9, 6, -12, -8. Well, here a negative and a positive. Well, this would be 1 over 0. Can we have 1 divided by 0? No. So this here is not possible, or really we can say it's not invertible. It will not have an inverse. Questions on this here? So really, if we looked at any of these here and found the determinant, if the determinant is 0, it's not invertible. We cannot have an inverse for it. So if we wanted to check it, well, for 2a, well, we could take its determinant, which would be our -3 times 4 minus 1 times 7. So we could say 3 times -4 minus 7 times 1, or 1 times 7. As if this worked out to be 0, then it doesn't have to work. If it gives us something different than 0, then it does. Well, 3 times -4 is -12 minus, which is -19. So will this have an inverse? Because if it's 0, then it will not. Any questions on this here before you find its inverse? Let's use the calculator this time. So to find the inverse of 2a, well, the first thing we'll have to do is enter the matrix in. So it'd be a 2 by 2, and we would have 3, 7, 1, and -4. We would just type it in. Now, once we get this typed in, we can go second quit. Second matrix A. Because we're going to call up this matrix. Now to get the inverse, well, we've been calling all the inverses a to the what? -1, yes? Do we have that key on the calculator? Because it is just the matrix key, what we've been using. We'd hit second and then that key. And if we have it here, we get this as the inverse. Well, all the ones we've had so far have been what? Fractions, yes? How can we convert it to a fraction? Math, enter, enter. And there's the inverse. So our 4/19ths, 7/19ths, 1/19th, and -3/19ths will be the inverse of this matrix. And the reason we got ugly decimals is because we divided each one of those numbers by 19. That's not a nice number. That number will not give us nice looking decimal numbers. Questions on this here? Any questions on any of this here? We're ready to look at the last thing. Solving systems of equations using inverses. Solving systems of equations using inverses. Whenever we have a systems of equation, we're going to write it as the product of two matrices. The first matrix is we're going to call our coefficient matrix, which will just be the numbers in front of x and y. And it's going to be multiplied by the variable matrix, which will be x, y. And we'll set it equal to b, the constant terms, what the equation is actually equal to. And then we will solve. Are there any questions on this so far? Okay. Now, this here is going to make this make a little more sense, because if we had an equation, ax is equal to b, to solve it, we would divide by a or multiply both sides by 1 over a, because here the a and a, 1 over a and a would cancel out, leaving us x is equal to b over a. We're doing a similar process here, because a times a inverse is 1, or the identity, which will give x. And once we solve or multiply a inverse times b, we will actually get the answer. So let's see how this actually looks. Using systems, or using these matrices to solve the system of equation, we need to write it as an equation with matrices. Now, our first matrix that we're going to write is just going to be the coefficients. So in the first equation, we have -7 and 2. In the second equation, we have 6 and 6. Now, this here is going to be multiplied by the matrix x, y. And we're setting it equal to what each one of those equations actually equal to. Any questions on this so far? I'm going to call this A in this matrix B. Well, if we multiply this left-hand side by A inverse, these two matrices here will simplify to the identity, essentially 1 for a matrix. And that's what I'm going to do, is I'm going to multiply both sides by A inverse. Because if we multiply both sides by A inverse, we'll get the matrix xy by itself. Now over here, we're going to multiply by the left for A inverse times matrix B. But at this point, do we know what A inverse actually is? Well, no, not yet. Any questions on this here before we plug this in? Because we could do this in the calculator. So if we go over here, we can plug in the matrix in for matrix A. Because our matrix A is our -7, so 2 by 2, our -7, 2, 6, and 6. Because this here would be matrix A. Questions on this here so far? Now what we can do is go second matrix, edit B, and matrix B is a what? 2 by 1. 2 by 1. And it is 18 and 0. Any questions on this so far? Second quit. Now what we're wanting to do is do the multiplication of A inverse and B. So to do that, we can go second matrix, A, but we don't want just A, we want A times second matrix B. And if we hit enter, we get -2, 2. So the product of A inverse and B is -2, 2. Questions on this here? Okay. So let's come back over here. So we have X. Now we're told that A inverse times B is -2, 2 is what we get. So what's the value of X? And the value of Y is? And that's it. And this will work with any system of equation or even number of variables in a system of equations. So if we have three equations with 3 variables, we can do this. 2 variables with 2 equations, we can do this. This doesn't work if we have 2 equations with 3 variables. We can't actually do it that way, but we can do it with row reduction. Let's see here, RREF, reduced row epsilon form will work. And that's really, if we're using matrices, the best way to solve any of these here. Questions on any of this? Let's look at one more. We'll look at this one here. Now, if we want to do this in matrices, well, we'll need to write out what matrices are. Well, the middle one is going to be XY. Now, our coefficients are going to be 7, 2, -1, and 2. And what it's equal to is -19 and 21. Any questions on this here? Now we can set this here as matrix A and this here as matrix B. We're going to multiply both sides by A inverse, which is really just going to end up giving us that the matrix XY is equal to A inverse times B. And we'll have to do it from the left-hand side because we'll multiply A inverse. In the first equation, we're going to multiply it by the left-hand side. We have to do it from the left-hand side for both. Well, at this point here, we can grab the graphing calculator and plug our 2 matrices in. So we can go second matrix, go over to A, which is still going to be A, 2 by 2, and we'll have 7, 2, -1, 2. And we'll type it in. Then we can go second matrix over to edit and matrix B, which is still A, 2 by 1. There we go. And it would be negative 19 and 21. And once we get those both typed in, we can do second quit. And we're going to want to do what? Matrix A inverse times matrix B. Yes. And we can type that back in, but we already have it typed in once, yes? So we can go up and select it, hit enter, and we get negative 5, 8. So that's telling us that, scroll down a little bit, xy is equal to negative 5, 8. So the value of x is negative 5, and the value of y is 8. And that's it. Any other questions or any questions on any of this here? Are we good with this here?